Well, welcome to lesson 9 on multiplying matrices. So in this lesson, we are going to focus exclusively on multiplying matrices and studying some properties about matrices as well. So the first caution I have for you is not all matrices can be multiplied together. So to determine whether or not the matrices can be multiplied together, we have to look at their dimensions. And two matrices can be multiplied if the number of columns in the first matrix matches the number of rows in the second matrix. Okay, and I'll show you a graphical way to remember that in a few minutes here. When two matrices can be multiplied together, the product is said to be defined, and the new matrix is called a product matrix, whose dimensions are the outside numbers. So I'll show you what that means in just a second. So this is a good slide to show you what I was referring to in the last slide. This one says determine if the product of the matrices is defined, if so give dimensions of the product matrix. So let's say we have matrix A whose dimensions are 2 by 4. Remember, it's rows by columns. And matrix B is 4 by 2, which is rows by columns. So is the product A times B defined? Well, A is a 2 by 4, B is a 4 by 2. The way to remember this and to tell whether or not you can multiply them, if these two inside numbers match, then the product is defined, and the dimensions then of the new product matrix are the outside dimensions that are left. So it's a 2 by 2 matrix. So that's kind of the way that you're going to be able to tell quickly whether or not you can multiply those matrices. So let's take a look at the next one. Is matrix B times A? What if we switch this around to make it a 4 by 2 multiplied by the 2 by 4? Well, if we look at that one, whoops, get rid of that. If we look at that one, B times A, B is 4 by 2, A is 2 by 4. Again, these inside dimensions match, so our resulting matrix is 4 by 4. So here's our hint. The two inside numbers have to be the same in order to multiply the matrices. And then what's left on the outside numbers is, those are the dimensions of your product matrix. How about this one? Is AB defined? Well, A is 3 by 2, B is 3 by 3. Inside dimensions don't match, therefore it's undefined. How about B times A? What if we put B first? Well, then we have the inside dimensions matching, and the result is 3 by 2. Letter C. If we go A times B, it's defined. The result is 3 by 5. However, if we do B times A, it is undefined because the innermost dimensions do not match. So how do we actually multiply matrices? We know now whether or not we can multiply them. How do we actually physically do that? So here's the process for actually multiplying matrices. You are always going to use the rows from the first matrix or the matrix on the left, and you will only use columns from the matrix on the right. And you add the elements that are in the corresponding positions and add them up. You multiply the ones in the corresponding positions and then you add them. So the row 1 elements in matrix A are multiplied by the column 2 elements in matrix B, and then those are added to find the corresponding element in the product matrix row 1 column 2. Step 3, then you're going to move to the next row and column. Row 1 elements, column 3 elements. So you get the element in row 1, 3. And this process continues. I know this is pretty confusing and doesn't mean much right now, but when I do an example here in just a second, this will all become crystal clear, excuse me. So it just goes on and on. So let's take a look. Here's an example. If I want to multiply matrix A times matrix B, first of all, let's figure out what it looks like. A is a 3 by 3 matrix and B is a 3 by 2. Rows are horizontal, columns are vertical. These match. My resulting matrix has dimensions 3 by 2. Okay, so let's go ahead and take a look at what that looks like if we go ahead and multiply. So we're only going to work with the rows from matrix A and only the columns from matrix B. So here we go. We're going to take row 1 times column 1. So the first element we want is we're going to take this element multiplied by this element, and we get a 6. Then we're going to add to that the second element. This element times this element. So we get 4 times negative 1, and then we add 2 times 0. Okay? So 2 times 3 gives us a 6. 4 times negative 1 gives us a negative 4. So we have 6 minus 4, which is 2, and 2 plus 0 is 2. So what goes in row 1, column 1 is the element 2. Okay, so now we're going to continue on. So let me go ahead and erase what I just did here. Oh, I didn't want to erase my highlights. So let me do this. Could I do this? Nope, that does the same thing. Yeah, it's okay. Let's just go ahead and erase that. So the second one, I'm going to take, let me get my highlighter back in here. We're going to take row 2, column 1. I think that's the order in which I did this, so let's double check. So row 2, column 1, nope, I did row 1, column 2. So let me just move this up, row 1 and column 2. Okay, so I'm going to take the first element, which is 2 times 2, add to that 4 times 4, add to that 2 times 2. So we have 4 plus 16 plus 4, which is 24. So now we're going to go to row 2, column 1. Okay, row 2, column 1, multiplying 1 times 3 plus negative 5 times negative 1 plus 1 times 0. Add those together, you get 8. Then we are going to move from row 1, column 1 to row 1, column 2. So our element in row 2, column 2 is 1 times 2 plus negative 5 times 4 plus 1 times 2. Add the results, we get negative 16. Now we're ready to move down to row 3, column 1. So element in row 3, column 1 is 3 times 3 plus 0 times negative 1 plus 2 times 0. Result is 9. Now we are ready for the very last one, row 3, column 2. 3 times 2 plus 0 times 4 plus 2 times 2. Hopefully you're catching on to what I'm doing here. I'm just taking them one at a time and multiplying them and adding the results together. So our ending matrix, if you look at the positions, the element in row 1, column 1 is 2. Row 1, column 2 is 24. Row 2, column 1 is 8. Row 2, column 2 is negative 16. Row 3, column 1 is 9. Row 3, column 2 is 10. Okay, so all you're doing, and you never do columns in the first matrix, only rows. You start with row 1 times column 1, and then row 1 times column 2, then row 2 times column 1, then row 2 times column 2, then row 3 times column 1, and row 3 times column 2. Okay, so you just work your way down. So here's a good chance for you to practice this. In this one, we're going to find B times A. So we want B on the left, A on the right. B is 4 by 1, A is 1 by 4. So our resulting matrix will be a 4 by 4 matrix. Okay, it's going to get a lot bigger here. So C will have dimensions 4 by 4. So here we go. Here's matrix B, here's matrix A. So row 1, okay, it might help to highlight this maybe. So here's my row, here's my column. Okay. So row 1, column 1, the element in row 1, column 1 is negative 15. Then row 2, column 1 is 0. Row 3, column 1 is 3. Row 4, column 1 is negative 9. Now we're going to move back up to row 1, column 2. That result is 10. Row 2, whoa, wrong thing. Row 2, column 2 should give me a 0. Row 3, column 2 is negative 2. Row 4, no. Row, there we go. Come on. Row 4, column 2 is 6. Now we're going to move back up again to row 1. Here, let me do something here. I need to freeze these guys so they don't move. There we go. Now we shouldn't have any trouble. Okay, row 1, column 3. So column 3, row 1. I labeled this wrong, so I need to switch this right now. This shouldn't be a 3, 1. It should be a 1, 3. So ignore that. It should be a 1, 3. a 2, 3, a 3, 3, and a 4, 3. So let me edit that. Glad I caught that in the video here. Somebody would have gotten chocolate tomorrow, right? So this one should be a 1, 3, and then a 2, 3, a 3, 3, and a 4, 3. And then over here we should have, again, a 1, 4, a 2, 4, a 3, 4, and a 4, 4. There we go. Clean that up a little bit. So it should be a 1, 4, a 2, 4, a 3, 4. Okay, so let's go back to what we were doing. So we're looking at row 1, column 3. So row 1, column 3 should be 30. Row 1, column 3, again, another error here. That must not have appeared there. Should be a 30. Row 2, column 3 should be a 0. Should be a 0. Am I messing this up? Row 2, column 3 should be a 0. I think I inverted some of these, so let me correct these as I'm going. So that one should be a 0. Probably have some mistakes in my final matrix then. And then row 3, column 3 should be a -6. Got that one right. And then row 4, column 3 should be 18. And again, I have an error there, so let me just correct that. That one should be 18. Row 1, column 4. So back up to the top again. We're in row 1, column 4. Should give us a 20. Yep, some errors here. Thanks for your patience on this. That one should be a 20. Row 2, column 4 should be a 0. Got a mistake there. And row 3, column 4 should be a -4. I think I inverted my last two columns is what I did. So that one should be a -4. And then row 4, column 4 should be 12. There we go. So now all we have to do is put all of these in a matrix, and I'm going to have some errors in here, I'm sure. So here's our first column, 15, 0, 3, -9. Second column should be 10, 0, -2, 6. Third column should be 30, 0, -6, and 18. Let me just make those edits in here, 30, 0, -6, and 18. And then the fourth column should be 20, 0, -4, and 12. There we go. So that is our resulting matrix for multiplying those two together. So the question is matrix multiplication commutative? What that says is, does the order matter? Is A times B the same as B times A? Well, let's check it out. So first of all, we're only doing rows in column A, rows in, matrix A times columns in matrix B. So if we're going to do A times B, we want to take 3 times -1 plus 1 times 1. So we get -3 plus 1, which is -2. That's in this position. And then if we do row 1, column 2, we get 3 times 0 plus 1 times 2. So that's 0 plus 2, which is 2. That's this one. Then if we go down to down row 2, column 1, we get -2 plus 3, which is +1. Moving over to the last position, we get 2 times 0, which is 0, plus 3 times 2, which is 6. So this is our resulting matrix, and we take A times B. Now when we do B times A, we need to do the opposite. We're going to take the rows from B and the columns from A. Okay, so you have to think about that. If it helps you, you can move. Maybe it'll help if I go ahead and write this one. So matrix A is 3, 2, 1, 3. So if I put that in there, maybe this will help. And you can visualize it a little easier. So we're going to take -1 times 3 plus 0 times 2. So that gives me just -3. And then row 1, column 2. That's not going to let me grab that, is it? Nope. So row 1, column 2 is -1 times 1 plus 0 times 3, which is -1. Row 2, column 1 gives us 3. There we go. 3 times 1 plus 2 times 2, so we get 3 plus 4, which is 7. And then row 2, column 2. 1 times 1 is 1, 2 times 3 is 6. Add them together, we get 7. So we can see that we get different matrices, so therefore it is not commutative. How about associative? Is matrix multiplication associative? Well, does it matter if we associate different things together? We're going to take A times B, take that result times C, and see if this matrix gives us the same one as if we take B and C first and then multiply it by A. Now notice the letters have to be in the same order. We're not switching the order at all. So once I do this product, I have to left multiply A. So here we go. First of all, I'm going to multiply A times B, those two matrices together. They give me this matrix right here. I'm not going to take the time to explain that. You can work that through on your own. Then I'm going to multiply that resulting matrix, the product matrix, times C, and that gives me this matrix. So I want to see if I get the same thing if I start out by multiplying B times C, and then multiply that result times A. So B times C gives me this matrix. So now I'm going to take A times that product that I had, and I end up with this matrix. And if you compare those two, it looks like we got the exact same matrix. So it is associative, but it is not commutative. So a couple of vocabulary words that you need to know. A square matrix is a matrix that has the same number of rows and columns. The main diagonal, a square matrix has a main diagonal of elements from the top left corner to the bottom right corner. That's called the main diagonal. The multiplicative identity matrix is the one that has ones along the main diagonal. Okay, so it's a square matrix. And the product of any matrix and the multiplicative identity matrix gives you the matrix that you started with back again. So if you take any matrix A times the identity, no matter which way you multiply it, A times I or I times A, you're going to end up with the matrix you started with. So it says find AI. Well, if we use what we just learned, we should get A. But let's go ahead and do the multiplication. So if I do the multiplication on this one, I'm going to take 4 times 1. I'm going to add to that -2 times 0, and I'm going to add to that 0 times 0. Well, the last two give me 0, so I just get a 4. And that's exactly what continues to happen. If I take row 1, column 2, 4 times 0 is 0, -2 times 1 is -2, 1 times 0 is 0, so I end up with my -2, and so on and so forth. So I do end up getting the exact same matrix back again. Determine the identity matrix. Well, this is a 2 by 3 matrix, so my identity matrix needs to be a square matrix that has ones along the main diagonal. Well, what size matrix would I need to multiply by? Well, remember this number here, this 3, determines what size my matrix needs to be. So it has to be a square matrix, and to multiply it, it has to match. So this has to be a 3 by 3 matrix. So the identity matrix is a 3 by 3 where you have ones along the main diagonal from the top left to bottom right, and there's zeros all around. So this one shows, it says the tables show the number of each type of dessert ordered from each of 4 waiters and the time to prepare each one. Use matrix multiplication to find the total amount of time each server spent preparing the desserts. I'm going to whip through this one pretty fast. So here's the 4 by 4 matrix. If you just put your brackets around these, this is what your 4 by 4 matrix would look like. This is a 4 by 1, and I'm going to go ahead and multiply those. When I multiply those, row 1, column 1, row 2, column 1, row 3, column 1, and row 4, column 1, I end up with this matrix. So that is my resulting matrix. Jen spent 15 minutes, Brent 21, Ted 21, and Oscar 7. That's it for this video. We'll see you in class.